Hey everyone, it's Dr. Calkins. Today we're going to do experiment 8. What's in a name at which we call? It's Shakespeare, Romeo and Juliet. So compounds have names. Just like every semester when I see students, I have to learn your name. It takes me several weeks to learn 70 plus students. And I only see you once or twice, maybe 4 times a week. As we get into this chapter, we need to be able to look at the face of an ion and think of its name. No different than what I do every semester. So everybody looks different, so everybody has different rules to follow. 2 major categories of compounds we're going to name are ionic, just means metals and nonmetals with positive, negative charges that crisscross or join together if they're equal. Covalent, a little bit different. Covalent is going to be Lewis dot structure kinds of things that we saw in the beginning of this lecture chapter. And then we can really break them apart into, do they have IDE endings because they're binary, only have 2 parts. Ternary, they have 3 parts or more, typically end in AT or ITE. Acids, we have some cute ways to help you remember those. That's with H+, could be binary or ternary there. And then binary covalent, one of the easier ones, we use prefixes to help us on those. So as we look at binary, our first category, we're going to go through just about 1 page per idea of the lecture. Binary going to be metals, and they're going to have the same name as the periodic table. Even though they're an ion, they're still going to have the same name as the periodic table. We just have ion, but that ion goes away when we put it with a partner. What's unique about binary is they'll end in IDE because they have a nonmetal partner that has a charge. We saw those IDEs in supplemental 5 back in our week 2 chapter 3. So the only way to get good at anything is to practice. And this lab is full of practice, so let's try some of that. A couple things that we can take for granted is charges of some of our families. So remember, if we were to do this a while back, what we would have done is drawn that staircase metalloid line that separates our positives from our negatives. Then we take advantage of that here. So everybody here is going to be a +1. All the way up and all the way down. Everybody here is a +2. It's what they want to be noble gas-like. I did throw in a couple of our transition metals that never change, so look for those there. And then here we have +3, and then a +4. And that would continue down the actual group family as well. We just don't deal with those much in this lab itself. As soon as we cross that line, everything changes. This is going to be no charge for the noble gases, but then we have our -1s, our -2s, our -3s, -4s, -5s, and so forth. So remember that applies for the entire family, up and down, as we saw several weeks ago. So we're just using those answers. That's basically our cheat sheet to do the bottom. So I'm going to do 1 or 2 examples from each page, and then we'll let you do all the rest. So we go down, do some practice. Here we have same charge, so just squish them together. Li and F, charges cancel. When we name it, we say Li is lithium. And we say not fluorine, but fluoride. IDE. That'll be the case for everything on this page. So as we do other examples, we'll find a trickier one. Let's go backwards. Remember, this is the partnership. So as we go down to something like this one here, pretty obvious to say that this is calcium and a chlorine atom. Remember, if you cross charges, you can always cross them back. Calcium is a +2. We'd expect that being in group 2. This imaginary one can go backwards. That's a -1. Name-wise, definitely calcium. Even though it's a calcium ion, we still say calcium. But now instead of saying chlorine, we say chloride. IDE ending is binary always. Let's jump down and do one more. Calcium and nitrogen here. So charges are different, so we say crossover rule, cross them. We're going to get a +6 and a -6 by doing that. It's doing the algebra for us. You don't even have to think about it. So calcium 3 times, that's going to be a +6 total. Nitride twice, that's going to be a -6 total. So again, it's not calcium nitrogen, it's calcium nitride. So that gives you a taste of binary. Spend some time now doing the rest. So hit pause and come back. All right, so on page 39, we're doing about the same thing, but now we're throwing a curveball. We're using our Latin system names. And keep in mind, you can cheat off of this, at least for the time being until you get better at it, from our supplemental in the back. So all of these are listed on that right edge column of supplemental 6. So Latin system, we have a high versus a low. That's an ic versus an os. Problem is, they're all different. So for example, iron with a 3 is ic because it's higher than a 2 that is os. So ferric and ferrous based on fer on the Latin name. A little bit easier is the stock system. They just tell you the charge in parentheses. A whole lot easier to think about in that scenario. So all of those are listed in supplemental 6. This is on page 195 in your lab book. Notice here's all of our 2s and 3s. There's the ic and os. Most of these are in that top region of the periodic table. So they're in this region here from chromium over to nickel. A little bit beside that, you get to the plus 2s and plus 1s. We're not really going to see gold in Intro Chem too much, but it's a 3 and 1. We do see mercury a little bit. It's actually a 2 and a 2, but notice that's over 2 atoms. So it's really a mercury 1 when you reduce. We do see a little bit of lead and tin, so 4s and 2s. They're in the group 14. We'd expect that. Just like with carbon would be a negative 4 above it, but they also like plus 2s. And then there are some transition metals that don't change whatsoever. So definitely this page, very helpful because it gives you all of those ions in one space by family. The back will also help you later with the acids, those are the ones in yellow. So page 195 can definitely be useful in this situation. So let's practice. I'll do about 1 per page to get you through a lot of these next upcoming pages. So here we have copper 1 and a fluorine with a negative 1. So those are perfect matches, so just squish them together. We get CuF. Name-wise, we have 2 names, Latin and stock system. So definitely this is copper 1. How do we know that? They told us. And then we need to know if every transition metal has a 2, and that's typically the case, a few exceptions, but take for granted that everybody has a plus 2. Copper here has a 1. So ic is higher, os is lower, 1's lower than 2, so this would be cuprous, not cupric. It's based on the Latin name cuprum, where our copper Cu came from in the first place. And then remember, it's not fluorine, because this is binary, it is fluoride. So everything on this page also ends in IDE. Just pay attention to who's high and who's low. Remember, if you have something like this one here and you're not sure, you can always reverse cross to get those charges to give you some clues. So take a few minutes to try this page, and then we'll move on to the next one. So transition metal is a little bit tougher, but now we're going to get to the T43, 8s and 9s, and these tend to be some of the toughest, unless you learn the pattern. So like we talked about in lecture, the T box looks like the letter T as we sketched it onto the periodic table. What's nice about the T box is it has 3 oxygens in the 8 ATE ending ions. The 4 box has 4 oxygens, and it looks like the number 4 written on the periodic table. So 4 box, 4 oxygens. And then the 3 boxes that remain for the halogens, they have 3 oxygens, so it's basically 3, 4, and 3 for the number of oxygens in the ATE ion. Coincidentally, phosphorus by itself is a negative 3, and so is phosphate and arsenate. Sulfur by itself is a negative 2, but even with 4 oxygens, still negative 2. It's a coincidence, but we'll take it. Halogens, negative 1 by themselves, even with 3 oxygens, still negative 1 by themselves. So even though these look creepier than normal, we'd expect negative 1, negative 2, negative 3 for their families, so that's nice. Unfortunately, this letter box is not a numbered box. It doesn't fit the same trend. We'd expect a negative 3, a negative 4, negative 5, and that's not the case. But it does repeat itself, negative 3, negative 2, negative 1, up here again, negative 3, negative 2, negative 1. So that's how the pattern works. Just remember this entire page is ATEs. So let's try some practice. So as we do that, same kind of ideas apply. If the charges are different, cross them. Cross them. So we get copper in front twice. We get carbonate once. So technically there's an imaginary parentheses with a 1 out there. If there's a larger number that's coming over, you'll get parentheses and a number. That way you don't get like 32 or 33 oxygens, you get carbonate 2 or 3 times. So clue that we need is this is a 1. So as we name it, we can say copper 1, because they told us copper 1. Every transition metal has a 2, and the fact that this one has a 1 tells us that it is cuprous, not cupric. And this would be carbide by itself, but this has got 3 oxygens. It fits in that 3 box because it's an 8. So instead of carbide, it would be carbon 8. All T43 ions end in ATE. That's the easiest way to survive this page. So hit pause and try these now. All right, on page 41, we have the same ions, but now we can take away oxygens, change it from ATE to IT. So always know that higher numbers are ATE, lower numbers are IT, and that can get you through a lot of quizzes and so forth, get you through a lot of struggles on deciding on multiple choice or true false kinds of questions. If you lose twice, notice you're still in IT, but we had hypo. If you're to gain more, you're still an 8, so 8's always higher. You can remember the, naming chemistry is always 8 up. This is the upper number of oxygens. And if you add 1, you get per 8. So let's try some practice on some of these derivatives of T43 ions. So we've been dealing with copper quite a bit, so let's just skip down one and think about something different, different pattern. So remember, make the split. So it's a little bit easy here to say that it's PbNSO3. For now, you can probably cheat up here and steal some answers, and that's fine. You can do that on just about every page of this lab. Sulfur with or without the oxygens is a -2, so that's nice. But notice this is a 1-for-1 match. If this is a -2, this has to be equal and opposite, so +2. If it was not a +2, there'd be parentheses, and there's not. So we already know, based on that lead is now a 2, because its charge is a 2. We also realize that every transition metal has a 2, but this is not a transition metal. This is a main group metal in group 14. And we'd expect 4 in that family, but this is a 2. So plumbum is lead in Latin. So this would be plumbus. It's lower. 4 is the higher plumbic, 2 is the lower plumbus. If this didn't have any oxygens, it would be sulfide. If it had 4 oxygens, because it's in the 4 box, it would be sulfate. This one has 3. That changes it from sulfate to sulfite. So ITE when you lose an oxygen. So plenty of practice. Hit pause and try it now. All right, so one more step in the T43 idea. You can add hydrogens. So the name stays the same, but as you add hydrogen, notice your charge diminishes by 1 because H is plus. So if you had a -3 but you add H, it goes to a -2. If you add another one, you get 2 H's, but now it's a -1. Notice the dihydrogen versus hydrogen, telling you how many hydrogens are attached. And then if we add all, we ended up with the acid name that we'll see on some subsequent pages. So everybody can do this. Just know that a few of them have some old names, so hydrogen sulfate is also called bisulfate. If you were to lose an oxygen, it could be called bisulfite or hydrogen sulfite. But again, that's a loss of oxygen from a 4 down to a 3. Hydrogen carbonate, also bicarbonate in that baking powder, old versus new name. If we have as many hydrogens that can fit, we get the acid name. That's not part of this page, but it is part of this idea that we'll see later. So let's try some of those. Here's not a copper one, so we can use this one again. So the numbers are different, so cross them. Anytime they're different, we can cross them. If they're the same and you cross them, you're going to have to reduce. So don't get too cross crazy. We do have iron in front. We have HCO3, and that brings over a 3 again. So the issue is we don't want iron, hydrogen, carbon, and 33 oxygens. We want this HCO3 3 times. So that's why we need parentheses. First time we've had to use them in the practice that we've done together. As we name it, definitely iron. Which type? Well, they told us that it's a 3. And then all transition metals like iron have a 2, but this one has a 3. And what's fun about that is 2 is low, ferrous. This is 3, this is higher, this is ferric. As we look at the last one, we can cheat up above if we want. We can do that on just about every page until we get used to it. But this is 3 oxygens. It is in the T box. That is carbonate, but it has hydrogen. So you could say hydrogen carbonate, or you could just say bicarbonate for short. Both of them are acceptable. So again, I'm going to write bicarbonate just to remember that these are interchangeable. So take a few minutes to try the rest. All right, back on page 43, we have the leftovers, just like with food. Sometimes they don't taste very good, and many of these are poisonous. They're not going to taste very good, but they do have the answers above. They might throw some transition metals at you, but everything you need to know for this page is up top, and it could have some transition metals from previous pages to deal with. But remember, supplemental 6 could definitely help with that. So let's practice some of these. These are the ones that are pretty much flashcards only, so there's no easy, fun way through a T4-3 pattern to learn them. So let's kind of keep that visible at the same time so we can see where to find things. So this looks like oxide, but notice this is a split. So go up top and find it. There it is. That's a O2 -2. We call that peroxide. So again, cheating a little bit now until we get used to these names later. Definitely have an Hg. But if the partner, O2 -2, what does mercury have to be to match? That gives us our options. -2 has to balance with a +2 because there's not more than one mercury there. If there was, there'd be parentheses because mercurous is a weird one. This is mercuric. And obviously it's mercury 2 based on its charge that we found. Got to be careful with mercurous. Mercurous is Hg2 + 2. So that 2/2 is a 1, and that's not what we have here. So take a minute to try this page with the exceptions. All right, as we move on to page 44, what we have here is acids. These acids are binary acids. The entire page will have H+, that's a given, that's acid. But these would come from IDE. So what we're going to see is if you have IDE, you would turn into a hydroic acid. So let's practice some of those. Again, because they're binary, they have H+. So we can cheat here and say H+, 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 all the way down. And even here we can have H+. So that's a given for acids. That'll happen on the next page as well. But what's unique is their partner. If we have the same match, that same charge, so squish them together into HF. But if this is fluoride as an ion, IDE, this will be hydro, fluor, and then ic acid. Fun way to remember this one, because it has hydro, ic, and then acid. If you remember myride, IDE, has hydraulics, intentionally spelled incorrectly, hydroic acid. Cute way to remember how to do these on this page. Try those now. All right, so definitely the toughest page of acids, maybe the toughest page overall, page 45. What's not tough is the hydrogen ion H+ all the way down the page. But these anions are based on T4-3. If you're T4-3, much like the transition metals, you're ic acid. If you're losing oxygens, you become an I. We saw that on a previous page, but now you're going to be an OS acid. So ic still higher, but now an oxygen's not charged, and then OS lower, not in charge, but again in oxygens. If you drop down, you stay OS, just add hypo. If you go up, you stay ic, but you add per. So use this pattern. Think about T4-3 and then go up or down to get the name. So this chart definitely going to help out on this page. Let's try one. Maybe one or two here. Here we have H plus and Cl. Those are a perfect match, so basically just squish them together, you get HClO. Nothing too fancy there. But we need to know, how does this fit the T4-3 kind of series, because that's the one that tells us, is it an ate that make an ic acid, or is it an ite that makes an ose acid? So let's find chlorine on T4-3 back on page 40. It was in the 3 box. If you're in the 3 box, you have 3 oxygens as an ATE. So let's go back and see what we have. We have only 1. So if T4-3 has 3 oxygens, we must have lost 1 and then lost another to get to its name. So we would call this hypo because we've lost 2 oxygens, and then chlorus because we've lost oxygens acid. So it's all based on T4-3. You have to know where to start to know where to finish. Let's jump down and try another. This one here's got different charges, so much like before, we can cross charges and get H3PO3. But then think about phosphorus. Is it in the T, the 4, or the 3 box? If you said 4 box, you were right. 4 box is an 8. This one has 3. So if we go up and we say now, this has 4 oxygens for phosphorus, we have 3, we must have jumped down to 1, and there's our name. So this is phosphorous acid. So take a few minutes to try the rest of these using that pattern and using the T4-3 table on page 40. So we tortured you with lots of tough ones, and then we get back to the easier ones at the very end. And these use prefixes. So fairly obvious to know that 1 is mono, 2 is di, tricycles have 3 wheels, 3. Tetra, the game Tetris, has 4 lines, so 4 there. And then a lot of these other ones are geometric signs that you would have seen for your driver's test. So pentagons like those school crossing signs, hexagons, heptagons, octagons. So octagon like stop signs. When I was younger, my brother said that if a stop sign had a white border around it, that they were optional, and that is not the case. 9 for nonagon, 10 for decagon. So just use those prefixes as we attempt some of these problems to the right. So we'll zoom in a little bit, and we'll try 1 or 2. So notice here it says dihydrogen. So that tells you how many H's. So H2. And then mono is 1, oxygen. So that's just the fancy name for water. Turns out you can buy these signs on the internet. You can put these on your lake or your pool and say, do not enter, dihydrogen monoxide, poisoning. And that's really just water. So it might scare some idiots out of your pool or your lake. Let's try another one. Let's try one that's in the reverse kind of order. So here we have a sulfur and 2 bromines. So sulfur is just sulfur. We could say monosulfur, but we don't really need to. It's kind of redundant. But we don't know how many bromines until we say, because this is Lewis dot structures. This is not cross-charging of any form whatsoever. So here we would say bromide, but that would just be 1. We have 2 bromines, so we need dibromide. Also notice IDE because these 2 are binary. So take a few minutes to try this page, and we only have a couple questions left. All right, home stretch now. Lots of busy work, lots of practice, going to be useful for the exam eventually. Page 46 question says, describe the difference between ionic and covalent. Just remember, ionic has metal positive, nonmetals negative. Covalent has sharing of electrons. So put that into words and what that means. Number 2 says, why are parentheses required around polyatomic ions? Well, in the case earlier when we had carbonate, we didn't want 33 oxygens. We needed that parenthesis to separate the CO3 so that we get 3 of those, not 33 of the last atom of the chemical formula. So put that into words there. Lastly, Greek prefixes. Why do we use them on binary covalent, like on the top of this page, and not anywhere else? Well, if you're covalent, you're sharing. And unfortunately, we don't oftentimes know how much we're sharing. Binary ionic, which has a metal, that's determined by charges. Those charges are predictable, so we know what numbers to expect, but with covalent we don't. So because this is sharing, we need to know how much is sharing because it's not always predictable. So put that in the words for number 3. And this very long, very busy lab is now over.